We are discussing about deep neural architecture, and in the last lecture we discussed how the deep computation is different from classical computations, and then we have considered different types of supervised learning problems or different facets of supervised learning problem in the context of deep learning architecture. Now, in the neural network there is a nonlinearity function that we know that is used, and those are also called activation functions, and we have seen particularly the sigmoid function that is used in the artificial neural network very often. But so the property of this sigmoid function is that it squashes numbers to range 0 to 1, and so it can kill gradients. As you can see, it saturates when the value increases or value decreases, and there the gradients becomes almost 0. And then it is best for learning logical functions, that is functions on binary inputs, but it is not good for image networks, and it is not zero centered also. So, there is another activation function which is called tan hyperbolic x. So, it is also ranging from -1 to 1, and it is also zero centered. It is zero centered, which is desirable, and still it has the problem of that it can kill gradients when it is saturated, and it is not as good for binary functions. This particular function, rectified linear unit, it is very popular in convolutional neural network in different neural architecture. So, the functional form has been shown here, that is you can see only positive half of the input, it is linear, and then for the negative half it is the value is 0. So, that there is a nonlinearity and the discontinuity at the value 0, that is first order discontinuity is there. So, but the advantage is that it does not saturate in positive region, and it converges faster than sigmoid and tan hyperbolic on image data, for example 6 times, and it is very computationally efficient. But it is not suitable for logical functions, for representing modeling logical functions, not for control in recurrent nets, not zero centered output, and if it is going into the dead region, which is the negative part, then it is not going to activate the filters or activate the gradient. So, so it stops there. So, there is a dead zone in this case. So, to avoid that, we can have leaky ReLU, so that you have a very small increase in the negative part also, the small gradient. So, it has those advantages that it does not saturate, converges faster, and the gradients will not die. Other kind of activation function like ReLU, we have also exponential linear units. In this particular graph, this blue graph is the exponential linear units which corresponds to this function. So, the benefits of all ReLU benefits are there, and it is closer to 0 mean outputs. Another nonlinear activation function which is called max out neuron. Here it is a maximum of 2 linear maximum of 2 linear combinations of inputs, W1 transpose x plus B1 and W2 transpose x plus B2. So, it does not have basic form of dot product, of course, it is nonlinear, and generalizes ReLU and leaky ReLU, does not saturate, does not die. Problem is that it doubles the number of parameters per neuron, and we have seen this standard architecture of one hidden layer neural network or 2 layer neural network, and another 3 layer neural network architecture, and sometimes this is called multi-layer or fully connected network or perceptron, and hidden layers are learned feature representations of the input, and these are deep features. So, with this actually I have talked about general features of neural networks and also deep neural architectures, but let me discuss the specific deep neural architecture which is very popular in various applications, and which one is convolutional neural network. In convolutional neural network, the convolutional layer that we need to understand, that is a hidden layer, And in the convolutional layer, what we have, that input is an image, say 32 cross 32 cross 3 image. That means, for example, it could be RGB, 3 channel RGB image, or it could be any other 3 components. And there is a filter. So this filter performs the convolution operations over this image. And size of the filter, sometimes it is called kernel also. For example, in this size, here it is given a typical value, say 5 cross 5 cross 3. So first thing, the filter extends the full depth of the input volume. So 3 is the depth in this example. So the filter has to span over the depth, and then what it does, it takes a dot product. So I will explain that. So it convolves with respect to the image, which means this filter slides over every point and computes convolution. That means the dot products with the input with the filter weights, and then produce that output at the central locations of that central pixel of that mask. So this is the example that you have 5 cross 5 cross 3 filter W, and it is placed within a pixel of image, and then it takes a dot product and then produces a value, and this value is the output at that point. So for example, in this case, you have 5 cross 5 cross 3 chunk of the image, that means 75 dimensional dot product you are doing, and there in the neuron, as you know that it is the dot product, and in the neuron there is a bias term. So then you add the bias term, and that could be also the output of the convolutional layer. So one of the feature of this convolution is that it is the locality, which means that objects tend to have a local spatial support. So this could be exploited using convolution. And the other feature is that weight sharing. Since you are convolving over all spatial locations, so the same weights are used, and finally you are generating the output. So if we consider that boundary conditions, that only pixels which are fully embedded, the convolution mask which is fully embedded within the image at those pixel sites, you are only considering output from those pixel sites, then the size of the activation map get reduced. As you can see, the filter is of size 5 cross 5. That means along height and along width, you have to leave out 2 pixels each at each edges, because those pixels are not fully embedded. So finally size would be 28 by 28. And along depth wise also, other planes are not coming into picture because they are not fully embedded. Only the central pixels, convolutions for the central plane, those are only considered here, because for those pixels only this full embedding is available. Say another feature of this computation, that it is translation invariance, which means the object appearance is independent of location. Now you consider that there are other filters. So there is another second, say, green filter of the same size, but its weights could be different, and it also produced another, we call it channel output. So it also produced another output, and if there are 6 such filters, you have 6 such activation maps, 6 separate activation maps, and you can stack this to get a new image of size 28 cross 28 cross 6. So 6 number of convolutional filters. So the features of conv layer or convolution layer we can consider, that is locality, which is the feature of having local spatial support for objects. Then translation invariance, where object appearance could be independent of location, and weight sharing, which means the units could be connected to different locations having the same weight, and equivalently each unit is applied to all locations, and weights of filters are invariant. This keeps the number of parameters small for convolutional neural network. Of course, since there are many such layers, finally total number of parameters will be quite large. Then each unit output of filter is connected to a local rectangular area in the input, and that is considered as the receptive field. So, as there is a nonlinear function in each neuron, so after convolution layer we consider that the nonlinearity at every point itself is considered as a layered response from the system, whose input is the output of the convolution layer, then it goes through the nonlinear stages at every pixel. So, it is a pointwise nonlinearity, and it increases the nonlinearity of the entire architecture without affecting the receptive fields of convolutional layer, which generalizes the model further, and ReLU is commonly used that I have mentioned. So, what is a CNN? It is a sequence of convolution layers and nonlinearity. So, you have a this is your input, you have the convolutional layer and also the ReLU, this is one layer, then another layer of convolutional layer and ReLU, second layer, and it goes on. So, CNN is sequence of such convolution layers and nonlinearities. So, let us also see what are the parameters involved in convolutional layer. Consider your input is of size W1 cross H1 cross D1. So, in my previous example, we have taken 32 cross 32 cross 3, that was the size of the input. So, value of W1 was 32, H1 was 32 and D1 is 3. And consider there are k number of filters. In the previous example, this value of k was 6, we considered 6 filters, and size of the filter is Fw cross Fh cross D1. So, in the previous example, we have taken 5 cross 5 cross 3 filters, which means Fw was 5, Fh was 5 and D1 is kept 3. So, you note that the depth wise the filter has to have the same number of channels what you have in the input, or same number of depth slices what is there in the input, because the idea of convolution layer is that the filter should be totally embedded within the input image, and that too at the central slice, and that is why the depth has to be the same, and then it would provide only single channel output. And then there is another parameter called stride. So, it is considering that the point where you are performing convolutions, so how the point could be separated in the grid. So, in the if they are adjacent, then stride is 1, that was the previous case. Suppose you leave one out of them, then the stride would be 2. And also input could be 0 padded on both sides to keep the size same. So, if you would like to include also the edge pixels or boundary pixels of the image, then pad the input with 0 and then perform this computation, and it would produce the output volume size of W2 cross H2 cross D2. So, what should be this output volume size? Now, these values are all related with the values of input sizes, like values of in W1, H1, D1, Fw, Fh, D1. D1 is not very important here, but W1 and H1, Fw, Fh, Sw, Sh and Pw, Ph, for all those values they will determine what should be the size of your output. For example, consider the value of W2, and as this is the expressions. So, it has taken care of striding, it has taken care of 0 padding, it has taken care of the size of the filter and complete embedding of the filters within the input. So, you observe that the number of depth slices should be the number of filters k here. And what could be the number of parameters? Since the parameters involves say the weights of the filters, and since there are the size of the filter is Fw cross Fh, so and cross D1, so that many number of weights should be there. So, it is Fw cross Fh cross D1, and if there are k filters, you have to multiply with k. So, we are assuming here that in the convolution layer all the filters of same size and all the filters of same size. So, the parameters as you can see Fw cross star Fh cross D1 into k, that many weights, and each neuron could have a bias. So, you can have k biases. So, your summary of this particular operations is that dth depth slice of output is a result of convolution of dth filter of the padded input volume with a stride and then offset by dth bias. There is another kind of layer in CNN which is called pooling layer. So, in the pooling layer it tries to progressively reduce the spatial size of the representation, that is its tasks, so that it can reduce the amount of parameters and also computation in the network. It controls overfitting, and pooling partitions the input image into a set of non-overlapping rectangles. So, for each sub-region outputs an aggregated value of the features in that region. There are two types of aggregation. One is max pooling, which considers maximum value. The other one is average pooling, which takes average value. So, it operates over each activation map independently. So, this is an example of pooling layer. You can see that the input was 224 cross 224 cross 64, doing max pooling with 2 cross 2 filters and stride 2. You are leaving one sample in between, that is a stride 2, and that is how the input size, output size is half of the input size. So, you have 224 cross 224, output would be 112 cross 112, but the number of depth remains the same. And the example here, it is showing max pooling. First, you have partitioned the input into 2 cross 2 rectangles, into rectangular sizes, blocks, and from there you are choosing the maximum value and you are replacing, you are forming your 1 pixel for each block. So, parameters which are involved in pooling, let us observe that. So, here input volume size is once again W1 cross H1 cross T1, and pool size could be FW cross FH with stride SW SH. So, output volume size is W2 cross H2 cross D2, and that is related with input parameters. So, W2 would be W1 minus FW by S plus 1. So, that is why that is what you are doing, and H2 is H1 minus FH divided by S, that is plus 1. So, that is the H2, and your number of depth remains the same as the input. What about number of parameters? As you can see, there was no weight, no bias, nothing. You are, it is without specifying anything, you can perform this computation. So, actually there is no parameter involved in this operation. It is just the computations that is providing you the output of the, it does not depend upon any parameter, and it is very uncommon to use zero padding in a pooling layer. Then we will discuss about the fully connected layer, which is also coupled with convolutional layers or CNNs. So, it contains neurons that connect to the entire input volume. That is why it is fully connected, as it is there in ordinary neural networks, and input volume to FC layer can also be treated as deep features. So, either it could be deep features or it could be the feature representation itself for a classifier. So, these are the two options for FC layer. There are various operations which are required for efficient training and testing of CNN, or for efficient computations of CNN, effective computation of CNN. One of the operation is known as batch normalization. So, it tries to condition the input and also the intermediate responses. So, what it does? It normalizes input activation map to a layer by considering its distribution over a batch of training samples. Consider, for example, you can apply a Gaussian activation maps, a Gaussian model there. Using batch normalization, you can improve the gradient flow through the network, and it allows also higher learning rates. So, your convergence becomes faster, and it reduces the strong dependence on initialization. This also acts as a form of regularization of the network, and batch normalization is usually inserted after fully connected or convolution layers and before nonlinearity. So, let me elaborate a little bit about this computation. As I mentioned, it normalizes activation responses of a channel of previous layer. And how does this normalization work? It subtracts the mean of responses of a batch and divides it by their standard deviation, and transforms the resultant output operation by scaling and translation by parameters A and B. In fact, this is also learned by the gradient descent algorithm. So, during test time, running averages and standard deviations of activation maps are used with the learned parameter for each channel at a layer. So, that is how the batch normalization was carried out, is carried out in CNNs. There is another operations which is also quite common and which improves the generalization of the model, and that is called dropout. What it does, it randomly drop out nodes of network at hidden or visible layers. It could be hidden or visible layers during training. So, dropout means it temporarily removes that node from the network along with all its incoming and outgoing connections, and it regulates overfitting, and which is more effective for smaller data set. It simulates learning sparse representation in hidden layers. So, implementation of dropout could be in this way, that you can consider that you can retain an output of a node with a probability p, and typically the value lies between 0.5 to 1 at hidden layers and 0.8 to 1 in the visible layers, which means input or output layers. So, weight becomes larger due to dropout. That is one of the effect of dropping out, that whatever weight you compute you learn, now the values could be, actual value would be larger, effect would be larger. I mean, you get large weight. So, you need to scale down that weight at the end of the training, and there is a simple heuristic that if your outgoing weights of a unit is retained with probability p during training, then you should multiply by p at the test time, or you can consider these operations during training time itself at each weight update, and then you do not require to do it during test time. So, you can use the same weight as you learn. So, with this let me take a break, and we will continue this discussion in the next lecture, where we will be discussing different types of convolutional neural networks, different kinds of architectures in my next lecture. Thank you very much.